Hello guys, we continue with matrix representations of L, I, angular momentum. Let's look at some motivations, okay? So if you learned previously, recall that if you have a matrix M, okay, acting on a vector, we over here I write it down in terms of a cat vector, and they produce eigenvalue lambda, and then we have another multiply with another eigenvector. This is the eigenvalue equation. I have been repeating this many times. Alright, eigenvalue equation, eigenvectors, right? Similarly, you can have it as a Hamiltonian acting on maybe cat psi, and then you have energy spectrum psi. Okay, depends on what you do. Psi n can just be interestingly equate them with n. Okay, if you understood psi n is as a function. So now this cat n live in some space. Okay, so in this case a Hilbert space, a vector space. Okay. Now if you look at, maybe I put here equation 1, this is equation 2. So from equation 1, you know that M can be usually represented by a matrix. So if it's a 2 by 2 matrix, then you produce at least 2 eigenvalue, and your eigenvectors has eigenvectors 1, and then you have eigenvectors 2. Okay, eventually you can write if this is like C, okay, matrix C, then you have C inverse multiply with M, multiply with C, you have D, and your D here is none other than your lambda 1, lambda 2. Okay, sorry, lambda 2. So this you call a diagonalized matrix. This is very well known. So if you change everything here in terms of M equal to the Hamiltonian, it means that you can also diagonalize your Hamiltonian. So you can write your Hamiltonian in terms of a matrix form. So this is what we're going to do with operator L square, LZ, and so many others. Okay, and I would like to introduce you, previously we also have L plus minus, which is Lx plus minus ILY. This is by right A definition. You can look back on the definition side. Okay, now for the example here, so whenever you have J equals to 1 or equivalently L equals to 1, that means your M is plus minus 1, 0. So you are now bound by your M is dependent with the values L. Then you can find the matrix representations of all operators. This is the usual operators arise in angular momentum, and then you can find the eigenstates. All right. Then usually there are orthonormal and complete bases, and you can use the matrix to evaluate. Eventually everything just become a matrix. Okay, but now we are going to understand what it means by this cat, so the shared eigenstate. Okay, so you see Lj0, your M is L1. So now you go back to at the front at the form of, so if you have L square Lm, then this means you have H bar square L plus 1 Lm. Okay, you go back by the original idea of eigenvalue equations of your Lz and L2. Okay, so now if your L is 1, it means that your M is plus minus 1, 0. So we expand this. Then you have L square 1M, which always give you 2 h bar square 1M. And then your LZ 1M become h bar M 1M. From here you can move further. How many states you have? 1, 0. That give you h bar 2, 1, 0. But another one, you also have LZ. You can have many. 1, 0 means 0, 1, 0, and then you have 1, 1. You have h 1, 1, 1. And then similarly you have LZ 1 minus 1. Then you have IH bar 1 minus 1. Okay, you see you have 3 sets of M, but respect to L square you only have 1 eigenvalue. So how you make it into matrix? So for L 1M 3 of the values, you have 3 by 3 matrices. Alright, and then you will design it such a way as follows. Okay, you can interchange the order. So the first one, if you have L square, so you will write this like, this is how you build up your matrices. Okay, so the first one is 1, 1, L square 1, 1. Alright, the second one is 1, 1, L square 1, 0. And the third one is 1, 1, L square 1 minus 1. See? Do you see? This is the change of your M. M entry. So next we move on. So below is you have 1, 0. So you change the bra side. 1, 1. So L square 1, 1. So you see you keep this part remain. So over here you only deal with the diagonal. Here and then over here sorry, let's skip that. Should be minus 1. Okay, so eventually you notice that this one, this part, so all of these, they are orthogonal. Okay, but the rest, how about the rest? So this one, all the red color, okay, will give you 0 because they are different. Okay, so what do you do with this? So you know that if you have 1, 1, this just give you h bar square 1, 2, 1, 1. Alright, so but it remains with the same other for all diagonal. So your L square is none other than 2h bar multiply with matrix 1 0 0 0 1 0 0 0 1. Okay. So I have give you example of the L square. You might want to try other operators. I will put it in Putra Blast. Okay, so you read for the other parts. Thank you.